Okay. Multiplication rules and conditional probability is what we're going to do for 4-3. So there's the first type of events that we're going to do are called independent events. Two events, we'll name them A and B, are independent if the fact that A occurs doesn't affect the probability of B occurring. So some examples of those types of things would be flipping a coin and getting a heads and rolling a dice and getting a 6. It doesn't matter if you got a heads or a tails here, based whether or not you got the 6 or not. Okay, so that's just one type of example. If I rolled a 6 and then rolled again, what's the probabilities of getting a 3? It didn't change based on the fact that I just got a 6. Okay, drawing a card from a deck and getting a queen, replacing it, and then drawing a second card and getting a queen again. So the main thing there for independent events with cards, cards or balls or anything, is replacing it. Okay, when two events are independent, the probability of both events are just the probability of each of them separately. Okay, so we'll do an example of this. So this is a nice big equation that you want. That did not work like I wanted it to. I tried to put little stop signs for myself so I know when to end. But for the next one, it looks like that's the first thing on there, so it doesn't matter. Okay, so when we're doing these things, replacing it and that equation. Okay, so that didn't work because the stop sign came up first. The probability of heads and a 4. So we'll use the multiplication rule for that guy. So we will do it in two different ways so we can kind of see how that works. So the probability of getting a heads, so a heads and a 4. So that would just look like if I'm writing everything out, probability of heads times the probability of a 4. So what's the probability of getting a heads on a dice?
A head?
Mm-hmm.
A
Heads or tails?
on a dice?
Oh, just kidding. No, not on a dice. On a coin.
Oh, okay. So, yeah. Because I was just like, what?
Sorry. What's the probability of getting a 4 on a dice? Sorry, I didn't really write that very good. 1/6. 1/6. Then I multiply them, and I'm going to get 1 out of 12. Okay, what that actually looks like if I'm writing everything out in my sample spaces is, hey, look, I could have a heads and a 1. I could have a heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6.
And then do you go over with tails?
Yep, then we would do the same thing. I'm not asking you to do it all with sample spaces. Sometimes sample spaces work out nicer, or not necessarily like writing them all out like this, but sometimes tree diagrams are going to be like your best friend. Okay, how many? I had 12 total options after I get them all listed. How many of those were a heads and a 4? Just that one out of 12. Okay, so I still just had 1 out of 12. So if you ever get lost, you really can just write out all of the possibilities. That is so always an option. Sometimes it's a really crappy long option, but it's still there. Okay, using the multiplication rule is just kind of that easy way to do it. Higher. Okay. If I have some cards, so I have a deck of cards. What's the probability of getting a queen and an ace?
Because we're talking about the deck.
Okay. A card is drawn from the deck and replaced. So remember, that is that keyword we're looking for. You have to do it. The second card is drawn. Find the probability of getting a queen, then getting an ace. So this replaced piece is the piece that makes it independent, which means we get to use the easy rule, which we haven't learned the hard rule yet. So the easy rule, probability of getting a queens, how many queens are there? 4 out of 52. I put that back, then how many aces are there?
What is PQA?
Which one, this one? Or this one? Queen and ace.
Oh, sorry.
Okay, so that's 16 out of whatever 52 squared is. If you wanted to reduce it here, if you have a calculator, you can just use that fraction piece. Otherwise, you can reduce it by saying, okay, 2 goes in here. So that would leave me with a 26 and an 8, 26 and a 4, 26 would go down to 13 and 2. So I could have 2 over then whatever 26 times 13 is. So that's a little bit shorter. 169 to 80, 98 to 98? No, definitely not. Okay, I'm going to write 26 times 13. Do you guys have calculators out? 26 times 13.
26 times 13.
Uh-huh.
388, or 338.
338, yeah, I was way off.
338.
Okay, so then that's that final thing. Okay, that is, for this, we definitely don't want to make our whole sample spaces for that, because that's gross. We don't want to have to draw out our little deck of cards every single time. Okay, balls. We're going to do lots with blue balls. So just get it over with. Say blue balls a few times. Laugh about it right now, because we're going to say blue balls a lot, okay? I'm going to say 2 blue balls a lot. Okay? Okay? So it doesn't work when I put my stop sign first. Okay, an urn contains 3 red balls, 2 blue balls, 5 white balls. A ball is selected at random and its color is noted. Then it's replaced, so we get to use our easy rule. Our second ball is selected and its color is noted. Find each of these probabilities now. So of selecting 2 blue balls. So what's the probability of getting a first blue ball? Get it over with. How many blue balls do I have? I have 2 of them. How many total balls do I have? 10 times. I put it back. How many blue balls do I have again? Get it over with. Oh my God. How many total? 10. Multiply. I have 4 over 100 or 1/20. Okay. What's the probability of selecting 1 blue ball and then 1 white ball? So if I get 1 blue ball, I have 2 out of 10. Times the probability of 1 white ball, 5 out of 10. You can reduce it whenever you want to. Just write out your original thing for me. But if you wanted to reduce it here, you could be like, oh, 1 over 5, 1 over 2. Hey, my answer is 1 over 10. Or you could like multiply it all the way out and then reduce it like we did here. Okay, selecting 1 red ball and then 1 blue ball. Okay, so 1 red ball, I have 3 out of 10. 1 blue ball, 2 out of 10. So I have 5 out of, not 5, how about 6 out of 10? 6 out of 100. Which one? God, it was, wasn't it?
I finally just watched it.
No, it was bad. It was really stupid. Okay, so 3 out of 50 for that guy. Okay. Hey, look, maybe I have my stop sign in the right place now. Okay, more than 2 independent events. So these same rules work if I was drawing 3 balls out of there. Okay, well, multiplication rule for those can be extended. A Harris poll found that 46% of Americans say that they suffer great stress at least once a week. If 4 people are selected at random, I need to fix that. Find the probability that all 4 will say they suffer great stress. Wow. I was typing fast, sorry. It didn't tell me it was spelled wrong. Great. We're going to grate some cheese. That they will experience some great cheese at least once a week. Okay? So yeah, I know this is spelled wrong. Whoever watches this in the future. Okay, so what I'm doing there is I'm looking for 4 people. So what's the probability that first person will suffer from great stress? Stop being gross. Okay, so 0.46. What's the probability the next person will get that? 0.46 times 0.46 times 0.46. So there's a couple ways, so you can type it all in just like that. The other way you can type that in is how many people am I looking for? That will be an exponent. 0.46, not times 4, to the 4th power. Okay? So these 2, you could do either one. Eventually, like if you're doing like a lot, like if you were doing like 10 of them, I don't think I'd want to make sure that I could fit 10 of those in a calculator because I feel like I'd probably not count right. So a 10 might be better there. Okay, so we just keep multiplying with whatever we get. Okay, dependent events is the next thingy we're going to go over. Okay, when the outcome or the occurrence of the first event is affected. Wow, I said that wrong. When the outcome of the first event affects the second event in such a way that the probability is changed. Okay, one affects the next. One affects. Wow, I should not type so fast. Examples: drawing a card and not replacing it. So the part that Jake hates is that we actually have to read those. Then drawing a second. Okay, selecting a ball, not replacing it. Not. Okay, being a lifeguard and getting a suntan. Those are pretty good chances, right? Having high grades and getting a scholarship. Parking in a no parking zone and getting a ticket. Those are kind of considered like conditional. The second one is based on that first one. And we will find some of those guys later on. Are you ready an example? Okay, sorry. I didn't mean to click that one. The suntan and scholarship pieces are not ones that we're going to use a lot. Is that comfy?
Yeah, it really is.
Yeah, I believe nobody else ever has either. Okay. Okay, so the next thing we're going to do is those conditional probabilities. So the way that we write conditional probabilities is really weird. So suppose a card is drawn from the deck and not replaced, the second card is drawn. What's the probability of getting an ace, then a king? Whoops, I don't really need that. Okay, so the way we write that is this thingy right here. Okay, that's red. The probability of getting a king given that the ace has already occurred. So this little vertical bar right here is usually how we say given. Okay, so the probability of getting a king given that an ace has already occurred. Okay, so basically what we're finding out for this piece is what's left over after A has already happened. Okay, so the general way we say that is what's the probability of B given that A has already occurred. So now let's actually do this with the kings and aces. Okay, so what's the probability of getting an ace? 4 out of 52. Okay, I didn't put that back. How many cards do I have left? No, I just drew one of them. 50 what? 51. How many kings do I have left? Did I draw a king the first time? Nope. So I still have 4 kings left. Okay, so that's basically what I mean by what's left after the probability of that first thing happened. Okay, so 4 times 4, 16 over whatever that gross number is. You'll use that gross number a lot because we'll do a lot of that. Just put it in your calculator. If you want to reduce it, make sure 52 times 51. If you want to reduce it, just make sure you're using that math fraction thing on your calculator. And that will automatically reduce it for you as well. 2652. And actually do 16 over that. And then do math frac. Math, hit the math button. And then hit the frac. I think it'll.
Oh, hold on, I did it wrong.
Okay.
Oh,
That's loud.
Four over 663.
Okay, so that's just as reduced as it possibly goes. So kind of depending on what it's wanting, this would be okay. You can also do it not as a fraction. I haven't done think about that. They might not want everything as a fraction. Okay, that vertical bar, if you ever want to type it, is underneath your backspace on most keyboards if it has a regular
What
keyboard.
is that bar do?
It's called given, so we'll read it as given. Okay. Okay, so this is your rule for these guys. So write that down, keep it handy. Okay, so we'll use that. At a university in Western Pennsylvania, there were 5 burglaries reported in 2000, blah, 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 16 in 2004, 32 in 2005. If a researcher wishes to select at random 2 burglaries to further investigate, find the probability that they will both have occurred in 2004. Do you know how hard it is to spell burglaries? It's weird. Am I saying it really funny? It's a weird word to spell. Yeah, it's weird. I had to spell it like 5 times in here. Maybe not. Maybe like twice. Yeah, it's weird. Okay. So how many total things did we have? So we have 16 and 32 is 48 plus 5. So I have a total of 53. Okay, so then if a researcher wishes to select at random 2 burglaries in 2004. So the reason why they're independent, or that they're dependent, that they're not independent, oh my God, lots of words in there, is they don't want to look at the same case. So I don't want to use 16 over 53 times 16 over 53 because that could possibly give me the chances of looking at the same case twice. Okay, so this is kind of, I wrote it out kind of how I would normally write it out if I was doing like a paper thing. So what we need to always say is, okay, what is my actual like letters that I'm going to use? Maybe I don't want to write letters and I'm just going to use words so that I know that I can read my words a little bit better. So what I need to find is the probability of my first case being in 2004. So that one is the nice one to find. So 16 happened in 2004 over my total of 53. Now, if I did choose one of those guys, how many burglaries would I have left to look at? So I'd have 52. And then if I had 16 and I chose one of them, I would have 15 left. Okay, so then I'm doing 16 times 15 over 52 times 53. And that piece you can do in your calculator. So I won't do that unless you have a calculator out. Okay? So that is what we're doing when cards are not replaced. So let's do some just card problems because you'll do a few card problems. Okay, so getting 3 jacks. I wish this like clicked just better. So the probability of getting 3 jacks is probability of getting the first jack times the probability of getting a jack given that the first card was a jack. And then the next thing will be written out. And you guys don't have to write this out. I just want you to make sure that you're able to read it. Some of the times I guess it'll ask you to write it out. Yeah, like kind of like this. So the probability of getting a jack given that the first 2 were jacks. So this is something how I would write it out because I might write like first was a jack. Okay, so the probability of getting a jack is I have 4 jacks out of a total of 52 cards. Just keep talking. Okay, the probability, okay, let's say I've already drawn a jack here. How many jacks do I have left? I have 3 jacks left. How many total cards do I have left? Not 52, 51. Times the probability of a 3rd jack, okay, I only have 2 jacks left. And I only have 50 cards left. Okay, so you're doing all that multiplication out, and you can do that in your calculator. And I guess I really don't care if it's a fraction or a decimal. Okay? Okay, so now we want to find the probability of getting an ace times the probability of getting a king, given that I already got an ace, and the probability of getting a queen after I got an ace, then king. Okay, so the probability of an ace, 4 out of 52.
Are we sure about that?
We are sure about that. We've done lots of those ones. Okay, probability of a king. How many kings are left? Still 4 kings. Oh my god. Probability of getting a queen. How many queens do I have left? I haven't taken a queen yet. How many cards do I have left? Okay, so that's what those guys look like. So
Say it, please.
no, don't say it. Getting a club. So we're going to do the probability of getting a club. If I can write out club. Then times the probability of getting a spade, given that I already got a club.
What do you do with your free
The probability I can at least draw a heart. I can't draw all the other ones. Given that I already had a club, then spade. Then spade. That's weird.
Wow.
Club. How many clubs are there?
She is right.
It's just me and you and her. Please.
Yes, but you and
On camera.
Brandon. What?
I don't make it in front of everybody.
How many spades do I have?
No, but Brandon makes
Oh my god.
You have a lot of space.
13. How many cards have I drawn? I've just drawn 1 right here. Nope, so I still say 51. How many hearts do I have? 13. Because I haven't drawn any yet. How many total cards do I have left?
50.
I've been drawing my 5s weird today. I don't like it. Okay, do that multiplication out in a calculator. That's weird. Getting 3 clubs.
I want to marry you.
So the probability of getting 3 clubs, I'm not going to write it all out. How many clubs do I have? I'm just going to keep talking. How many clubs do I have left? 12 out of 51 total cards. How many other cards do I have left? 50. And you're going to do that multiplication out too. Really?
You should save these videos and then like our 10th reunion, we just come back and watch these.
That's fine.
Listen to
Yep.
the audio.
I'll have you guys do that. I'll make you do math for your 10th reunion.
No, just want to listen to
They will still be on YouTube, I imagine. Okay, so conditional probability. Box 1 contains 2 red balls and 1 blue ball. Box 2 contains 3 blue balls and 1 red ball. A coin is tossed. If it falls heads up, a ball from box 1 is drawn. If it falls tails up, a ball from box 2 is selected. Find the probability of doing the red ball. Okay, so the easiest thing to do for these ones is tree diagrams. They can be your best friend. You want to see what else I wrote?
Yeah.
Because you don't have it.
Have any friends?
Okay, so the first thing I'm doing is flipping a coin. That's what I was going for. Okay, so the first thing I could have a heads or a tails. Okay, so if I have a heads, then what are my options? So I could have, where am I? If it falls heads up, a ball from box 1 is drawn. So then I need to go, okay, box 1, do I have this up here? Okay, so box 1 has 2 red and 1 blue. So I could have red and blue, but the probabilities here are 2 out of 3, and the probabilities for blue is 1 out of 3. Okay, the probability here was 1/2 and 1/2. So now I'm also going to do for tails, I'm looking at box 2. So I would have 3 blue balls and 1 red ball. So I would have blue, I'll do on bottom again. Blue has 3 out of those 4 things. And then 1 has 1 red ball. Red is 1 out of 4. Okay, so then to get each of those things, we're going to actually be multiplying. Are you guys draw my tree diagram with me? Okay, so the way that these are actually written out is
Wait, why is that H1 half?
so I should have wrote the probability of H equals 1/2. I'm going to write those out too. the probability of tails is equal to 1/2. What do I, tails?
Cells.
How?
The cells.
Tails. How do I say it? Am I saying it wrong still? Tails. Okay. But here, the weird part about this red was that it's actually, so it's still 2/3, was that it's the probability of red, what? Given that I have heads. Stop it. Okay, this one is the probability of getting a blue given that I had a head on my coin. Is that better or is that just... Okay, the probability of getting a red given that I had a tails for this one is equal to 1/4.
What is it at the bottom? Is that BH?
Which one? This?
No.
Right there? There. B given H. Okay, this one is the probability of a blue given that I had a tails is equal to 3/4. So that's what those guys actually look like when you write them. Okay, sometimes they just take a long time to make. So find the probability of drawing a red ball. What is so funny? Oh my God. Do you guys have this written down?
I'm working on it. I
Okay.
don't know the last one.
Okay. Okay, so now what we have to do to actually find the probability of getting those red balls is that we actually have to multiply those probabilities first. So we're going to do the probability of heads times the probability of red given that heads happened.
That's what you do with your time.
So it's going to be 1/2 times 2/3 is equal to 1/3. Then I'm going to do, hey, the other thing that I need to look at for red balls was the probability of tails times the probability of red given that tails happened. And that one is 1/2 times 1/4. 1/2 times 1/4 is 1/8. So let me make sure I had some of those numbers right. Okay, that's fine. They just didn't reduce their fractions. Okay, so those are the ones I care about just because they had red in this guy. So now what I'm doing is I'm adding those guys up. Okay, so I'm adding the probability, I'm not going to write all that out because that's messy looking. It's just 1/3 plus 1/8. I need a common denominator. Okay, that's about the grossest piece of it. If you do this in your calculator, you can just type in, like in fractions, 1 divided by 3 plus 1 divided by 8, math frac, and then it's not like the fraction-y piece of it that's going to get you. So anyway, if I had a common denominator, this would be 8/24 plus 3/24 is equal to 11/24. Okay, so that's what the answer is for finding the probability of those red ones. Sometimes we just don't want to do that much work because that is gross sometimes. Maybe. And this one I didn't even put my little animations on here. So if I just want to know the probability of the second event occurring, so this is kind of what we're going to look for right now. So let me leave that up there so we can continue looking at that tree diagram. I don't remember what it was now. Okay, so make sure you write this formula down. Can you read it over my writing? So we want to know how to find this given piece without having to draw a tree diagram.
So we have to find.
So if I just asked, what's the probability of getting a red given that you've got a tails? That one was pretty nice from the last question. Like you could have found that fairly easily. Sometimes they're just gross.
Start off so like nice, and then you start getting into a lesson, and then it just like makes me want to beat my head on.
Yeah, because if I started off with the gross stuff, you would feel like that right away. And I want you to feel nice about yourself for a while. Okay, so let me write this over here. Probability of B given A has already happened is equal to this guy. So the things that we need to know is, hey, what's the probability of A and B? Well, in this case right here, that would have been our 1/8. The probability of A happening would have been the 1/2. Okay, what's 1/8 divided by 1/2? That would have just got us this 1/4 on this piece right here. Okay, so what we're actually going to do then is they're not going to give you all of that information that we had for that last problem with the heads and the tails and things. Okay, main thing is that we need to say what our letters are for. So let me write this down. Probability of A and B over the probability of A. Oh, I think I actually put it up there where I needed it, but. Okay, so a box contains black chips and white chips. A person selects 2 chips without replacement. If the probability of selecting a black chip and a white chip is 15/65, the probability of selecting a black chip on the first draw is 3/8. Find the probability, oh my God, I did it everywhere. Find the probability of selecting the white chip on the second draw, given that the first chip was a black chip. Okay, so that is like tons of stuff in that question. Yeah, so the first thing you'll need to say is, hey, what do I want my chips to be named? B, how about B and W for black and white? Okay, maybe. Okay, so that's just kind of, you'll start with that. Whoops, no, I want to go back. I saw my stop sign and I didn't stop. Okay, so let's actually use that. So what we're looking for is, what's the probability of selecting the white chip on the second draw given that the first chip was black? So that's kind of that key sentence that we actually have to figure out. Okay, so I need to know what's the probability of the black and white happening. We know that one. The probability of the black and a white chip getting selected is 15/65. No idea. Poker chips, you would just have a lot of poker chips. I don't know why you'd only have 2 colors of poker chips. And then the probability of A, which is in this case the probability of a black chip. Me? Is 3/8. I have a lot of poker chips over there actually. Is 3/8. Now it's like, okay, where do they go at in my formula? So I'm going to have, basically right here, I'll have 15/65 times 3/8. Okay, remember our fraction multiplication rules that, did that work? No, okay, that's kind of it, that's weird. Okay, so remember our fraction multiplication, that would be the same thing as 15/65. We're only flipping the second one, 8/3. Reduce where you can. So 3 goes into 5, 40, that doesn't help much more. Okay, so type in this stuff in your calculator. So I'd have 40/65 would be the chances of getting a white chip on the second draw, given that the first chip was a black chip. 8/30. Okay. So that's what those guys will look like. So those are the conditional probabilities. So this little piece right here would be, if it asks you, find the conditional probability, that's what you'd be looking for. Okay, so we're just going to go through a couple of those and read all the gross words and figure out how to kind of get rid of all the gross words. Have I really talked this long?
Yeah.
Oh my God, I'm sorry. I'll hurry up. We'll try to hurry up. No, we're not done. We're not as far as we were. Okay, I'll give you less problems. Okay, the probability that Sam parks in a no parking zone and gets a parking ticket is 0.06. That's that and part up here, so I'm going to have 0.06 on top. Parking ticket, oh my God, I've spelled everything wrong. And the probability, it does have spell check.
Parring.
Parring is a word, I guess. Maybe if we're golfing. The probability that Sam cannot find a legal parking space and has to park in the no parking zone is 0.20. So that is just right there. That's that PA. So it's going to be over 0.20. And that will be my probability that I got a, let's say T is ticket, not ticket. T is ticket, and N is no parking. With a K. So that would be my probability of getting a ticket given that I parked in a no parking zone. So just whatever that happened to be, 0.06 divided by 0.2. Did I do a stop sign here? I did. So I don't know what that division is. Okay, a recent survey asked 100 people if they thought that women in the armed forces should be permitted to participate in combat. The results of the survey are shown. Find the following probabilities. No, I want this little chart thingy that I put on there, that I know I put on there. I just didn't put it in the right place. Okay, so the respondent answered yes, given that the respondent was a female. I like these charts. They're a little bit easier to look at for these given things. And sometimes I just like to make charts for myself. Okay, so given that the respondent was female, I'm only looking at female peoples.
So the yes is like 8 out of 50.
So 8, I had total 8 yeses out of my total of 50 females. Okay, so 8 out of 50. Okay, I don't have to use any really kind of special rules that I have to think about. It just kind of is more intuitive with those charts. Given that what are the chances that the respondent was a male, given that the respondent answered no? 18 out of how many people answered no? 18 out of 60. So make sure you're just looking in that right column, that correct column, not right. Okay? And there's at least probabilities then. Let's do some at least probabilities. At least probabilities, you use complementary events. You remember what complements were for something? So complements were like 1 minus whatever it is. Okay, so.
Like in our variance.
Yep. So a game is played by drawing 4 cards from an ordinary deck and replacing each card after it's drawn. Find the probability that at least 1 ace is drawn. So what we actually have to find out, the complement of at least 1 ace, is that there's no aces. Okay, so no aces is the complement of that. Okay, so remember we're subtracting from 1. So let's go back and do that. Since I didn't see my stop sign, I need to put it somewhere bigger. Okay, so what's the probability of no aces happening? How many cards are not aces in a deck?
Like 40 something.
48 out of 52. How many cards am I drawing? 4. I'm going to do this 4 times. Times 48 out of 52. Yes, and I am considering that they're replaced each time. I believe. Let me check that out real fast. Pretty sure that's right. Yeah. Okay, so the easy way to do this would be 48 over 52 to the 4th. And then we're going to subtract whatever this is from 1. Yep, and if you just want to type those in for those at least dudes, it's 1 minus the complement to the whatever power, however many you're doing.
.27397500009.
Was it 0.027?
Yes.
Okay.
No, 0.27, sorry.
Okay. So that's what you're going to get. Okay. I was going to do one more. Do you want me to do one more of the at least ones?